All right, start with a quote here from Kierkegaard. Life is not a problem to be solved, but a reality to be experienced. I think that, it's sort of a quote that's been summing up what I've been thinking about recently. So, yeah, I think it's a nice one. What we're going to look at today, though, is kinematics, and we're going to look at differential equations in kinematics. So, I think the best way to do this is to just explain it using an example problem. So, here's our problem. The acceleration a of an object is given by a equals negative v plus 1 squared. It's also known that when the time is 0, the velocity is 10, and when the time is 0, the position is also at some point 0. And our job is to firstly find an expression for the velocity v of t, and then secondly find an expression for the position x of t. And just this note down here as well says this problem involves variable acceleration, because you can see that the acceleration depends on the velocity of that particle. So no, we can't use our standard constant acceleration formulas anymore, because the acceleration is not constant. So what I'll do, as usual, I'll sort of play the video through just with minimal talking, and then I'll go back and explain things a little bit. What I really wanted to do is for you to get a feel for the different kinds of graphs and what they look like, and how we can hopefully see how we move from one to the other, but then we're going to plot that motion of a point P on a number line, so you can really get a sense of what's actually going on. So start with that. So the first thing is to look at the graph of A, which looks like this, and this shouldn't be too surprising. This is just a quadratic. We've got our V axis and our A axis. So acceleration equals negative V plus 1 squared. So basically that just means when the velocity is negative 1, the acceleration is 0. So if you've got some particle and the velocity of that particle is negative 1, say meter a second, then the acceleration of that particle is 0 at that point. Okay, and then what we need to do is let's actually think about the motion of this particle. So if we have this point P here, let's just call this the point P. This green arrow represents the velocity at some point. And at the start, this is going to move really quick, but we know from the question that the velocity at the start is 10. So if we play that and we draw the velocity time graph, we'll get something like this, and I'll explain where this comes from in a moment, but take my word for it that the velocity time graph will look like this. When the time is 0, the velocity is 10. So when this t goes to 0, you'll notice that the length of this green arrow will get quite big. And remember, just size is the length of the arrow is just representing the size of the velocity. So you've got to watch very carefully here. But as we start, hopefully you saw that little bit there as it started at 0. Maybe I can go back a little bit. There we go. As time is 0, that length of that green arrow is 10, because that corresponds to that point there. And then we can see that the velocity decreases, and then it swaps direction because it becomes negative. And then so velocity is a vector, so it has a direction. So now our point P is traveling in that direction. And you can see that it's asymptoting along that value, negative 1. I can tell you that this velocity value down here, or the asymptote, is going along at negative 1. So that's interesting in itself, I think. And then what we can do is we can think about the position time graph, and that should be an x. I thought I fixed that, but I didn't. We're now looking at the position time graph. So this is now x versus t. And so we get this situation. And I'll explain where this blue curve comes from in a second. But we end up, you can see how the position is shown by that curve. Okay. The next thing to do is to think about how we got those curves. Like, how did we actually work those out? Hopefully the first one's not too bad. But the next one is to say, all right, how did we work out the velocity? How did we get the velocity function from the acceleration function? And what I would like to point out is that we know that acceleration is the change in velocity over time. So if we were to integrate, if we'll firstly replace a with dv dt, and then integrate both sides. So let's see what that looks like. You might need to pause and just sort of flick through this here. But just on the left now, I've got dv dt is a. Separation of variables, you'll get something that looks like that. And then you integrate both sides, and you'll get that. So we're integrating both sides now. You'll get something like this. If you integrate that correctly, you'll get that. And this isn't a video about how to do the integration techniques. We've spoken about that otherwise. And then if you sub in those initial conditions, to get rid of the negative firstly, sub in the initial conditions, you'll get c equals 1 on 11. And so you get your v of t function if you rearrange for v as 11 on 11t plus 1 minus 1, which was that green function we saw before, which is why it's in green, right? It's a sort of hyperbola with an asymptote at v equals -1. And then having gone through the steps here, but if you integrate that using a similar process, you get the position function, which is this function here, which is in blue. So I think that's interesting enough. I kind of ended up explaining that as I went through, didn't I? So maybe there isn't much more to say. I think I just want to go back to here though, just to the velocity graph. If we look at this one here. Okay, so we're starting off with a velocity of 10. So because we know, firstly, that our position is 0 when time is 0, we know that we're starting here on our number line. And then as, as the velocity, we start at a velocity of 10. As time passes now, we can see that the velocity clearly decreases. And so if we just slowly play that at this point here, you see how it swaps direction. So somewhere there, the velocity is 0. So the point's actually not moving, because you sort of saw, if we go back, it starts moving to the right because the velocity is positive, and then the velocity changes to be negative. And then eventually it asymptotes towards having a velocity of -1. And now that should be interesting, right? Because if we play this out, if I play it uniformly, you can see that point P is traveling at constant velocity. And if there's constant velocity, there's no acceleration. So just to take it back a step, if we're back here, if the velocity, let me go back. If the velocity is -1, the acceleration is 0. And so that's eventually what happens to our point. That happens to our point as we start traveling, as t gets large, it just travels at a constant velocity of, say, 1 meter a second. And then, just to really link it with the position time, remember this is position now, we start at the point 0, 0, and then we move to the right a bit. At some point right at the top there, the rate of change of position is velocity. So our velocity goes to 0 wherever there's a maximum on this function, which, as we said, we can see the curve swaps directions there. So around when it gets to a position of about 1.5, it swaps. So then we get that, and then it travels out in that direction. And you can sort of imagine that the gradient of this position time graph becomes almost linear, which means it has a constant velocity, for values larger, for large values of t, which is why you can see that the position changes at a constant rate, which is its velocity for large values of t, which means its acceleration is 0. And so, after all that, we can sort of see the integration techniques as well, and we can see that that's our position function. Now, again, this wasn't a video on how you need to go off and hopefully do some integration techniques in terms of how to derive the velocity and the position curves, but I think this hopefully gives you an idea of the motion, right? I think when I was learning this the first time, I really didn't have a clear concept of what's actually happening with the point. Like, all of this is related to the motion of some object. And so to be able to see that object is really what I was going for in this video. So if you found that useful, give us a thumbs up, like and subscribe, all of that stuff. If you need any private tutoring, let me know. And if I made any errors or anything like that as well, let me know as well. The main goal here is to make sure we're getting things right and helping people with their special studies. So good luck, and I'll talk to you soon.